Here's a good wintertime problem for you. It says there's a furnace that ignites and raises the temperature in a house from 15 degrees C to 21 degrees C. What fraction of the original air molecules are pushed out? So some of the air is pushed out? Sure, you bet. So then, okay, we've read the problem. So now what are we going to do? We got to draw that picture, right? So we're going to draw a picture, and this says this is a house. So now we have to draw a picture of a house. Oh boy, you know how pictures are. This one is a blue house. Do you mind a blue house? Okay. Here's the blue house. Ah, it looks awful one-dimensional. Let's make it a little better than that. We'll give this a roof, like so. Now it looks like a Monopoly piece. Let's put some windows in it. Here's some windows. These are the good kind where you can actually see both in and out. Isn't that nice? Okay, sorry. So this is the house in condition number 1, 15 degrees C, a little cool. And so what's going to happen is the furnace comes on, kicks up the temperature. There's therefore a second condition. So I got to draw the house now in the second condition. Could I just put this on repeat and have it? I don't think it works that way. Let's try to draw this house again and see what's happening here. There's the house. Here's the windows. Same house, isn't it? Ah, amazing. Yeah. Okay, it says that these temperatures, we'll call these conditions 1 and 2. This one is condition 1, and just to make sure you can see this better. Okay, condition 1, and this is condition number 2. And so what's happening in conditions 1 and 2? Well, it says here that for condition number 1, the temperature in condition number 1 is 15 degrees C. So T1 is 15 degrees C. Now I do a funny thing. Whenever I see temperature in degrees C, I almost immediately convert it to kelvins because that's the absolute temperature scale. And it's really handy because often if you don't do that conversion, you get a wrong answer. So we're going to try to get a right answer here. So here we go. How do you get to the Kelvin scale? Well, you add 273 to this. So then this becomes 288 kelvins. Condition number 1. Condition number 2, it says T2 is 21 degrees C. And so now if we can add our 273 to this, we get 294 kelvins. Okay, good. All right. How do we solve this? Oh, what does it want to know? It says, what fraction of the original air molecules are pushed out? Okay. So how do we get the fraction of air molecules? Air. This is a gas. So this is a perfect gas problem, isn't it? So what's our perfect gas relationship? PV equals nRT. Right? Okay. That's good. So then we can say P1V1 is N1RT1, isn't it? Because it's true in all cases if this is a perfect gas. So it's also true here. P2V2 is equal to N2RT2. Okay, boy, it looks like a lot of variables, doesn't it? And the only ones that we know are the T1 and the T2. Oh boy, we might be in trouble. Then again, let's just work it through and see what it is that happens, because every once in a while, nice things occur. So then, what are we after? We're trying to find out the amount, the fraction pushed out. Fraction of air pushed out. So some gets pushed out. How do we get the amount pushed out? Well, what do these things mean? P1, P is the pressure, V is the volume, N is the number of moles. That's related to the amount, isn't it? Moles. Where does that come from? Are those furry things that burrow in the ground? No. Chemistry adopted that name. I'm not sure why, but they did. So they adopted that name, and that is related to the amount of stuff. So if we want to get the amount pushed out, we'd have to say N1, which is what was there originally, minus N2, because that's now what's there in the second condition. N1 minus N2 gives us the amount pushed out. To make that a fraction, we need to divide this by N1. So that's what we're after. So how do we get there? What's N1? Well, we just solve this perfect gas equation. And N1 is P1V1 over RT1. And so that's good, that's N1. N2, P2V2 over RT2. N1, P1 V1 over RT1. Does that look like kind of a mess? Yeah, it looks kind of messy. But there are some simplifications. So what are the simplifications? Well, the problem tells you one of them. It says the pressure remains atmospheric. That is, the atmospheric pressure is still the same. It didn't change when you turned your furnace on, right? Your furnace didn't affect the overall atmospheric pressure. No, not at all. It affected the temperature inside the house. That's it. So then what that tells us from the problem statement is P1 is equal to P2. Great. What else? Well, we can tell by looking at the diagrams. See how the diagrams are handy? Looking at the diagram. This is the same house, isn't it? So what volume of air are we talking about? Same volume. Same house, same volume. So you can say that V1 equals V2. Well, isn't this nice? Let's start out by simplifying this and then watch what happens, because it's really fun. We'll divide this P1, V1 over RT1 into both of these two terms and say this is 1 minus P2, V2 over RT2 divided by P1, V1 over RT1. Now here's where it gets really fun, because now if P1 is equal to P2, then those go away, don't they? If V1 is equal to V2, then those go away. The R's are just a constant. So those go away. Everything goes away except the T's. So this is 1 minus T1 over T2. How did that happen? Well, this is a fraction divided by a fraction. You invert and multiply, so the T1 comes up on top. 1 minus T1 over T2. Looks pretty easy, doesn't it? Because we know T1 and T2. And here they are. T1 is 288 kelvins, so this is 1 minus 288 kelvins divided by 294 kelvins. And so then that turns out to be a plain old number, which is 0.0204. If you were to express that as a percent, that's 2%. Does it seem reasonable that 2% would be pushed out? 2% of the air molecules would be pushed out when a furnace goes on? That might not be too bad, but if it said that 20% was pushed out, if we made a mathematical error saying 20% of the air got pushed out, you'd say, no, that's not going to work. 20% of the air is too much. So 0.0204, 2% of the air is pushed out. That seems like it passes the test of reasonability. Okay.